This TI DLP Labs video will cover basic DMD information associated with mechanical design, DMD mounting basics, and DMD electrical interconnects. The details of a specific DMD design will not be covered, but information will guide you to detailed mounting concepts on TI.com. The detailed concepts include assembly and part drawings as well as 3D CAD models. Before covering the DMD mounting information and how to locate the detailed information, it is helpful to understand some basic information about DMDs. The basics include different package styles, typical DMD features, types of electrical interconnects, and what is meant by a package style or family of DMDs. DMDs are available in a wide variety of array sizes, resolutions, and performance characteristics. DMD packages range in sizes to accommodate a 0.2 NHD to a 1.38-inch 4K UHD DMD. DMD sizes and resolutions include a 0.47 4K, 0.65 1080p, 0.8 wide UXGA, 0.95 1080p, and many other sizes and resolutions. The many package styles utilize three types of electrical interconnects. DMDs with board-to-board connectors utilize board-to-board connectors in the system also. DMDs with micro pin grid arrays utilize sockets. And DMDs with land grid arrays utilize interposers. DMDs do not utilize industry standard packages, and as a result, all except the board-to-board connectors are a custom design. It is worth noting that DMDs with the same series designation are a group or family of DMDs that share common features. DMDs that have the same series designation use the same mounting concepts. Type A DMDs do not share the same common features as those with the same series designation, but have common features within the same ceramic size. DMD features are defined in the mechanical ICD drawing and include the array of micromirrors. The array size depends on the mirror pitch and resolution. The window glass protects the micromirrors. The ceramic base supports the array and incorporates the mounting datums. The location of the array is parallel to a plane established by the datum A features but does not lie within the plane. The datum A is defined by areas and not visible features on the ceramic. The location of the array in the XY axis is defined from datums B and C. In this case, the datums are a hole in a slot. Other DMDs have open slots or defined areas on the edge of the ceramic. The datums A, B, and C are used to position the array in the optics when mounting the DMD. The electrical interface defines the area on the back of the DMD where the electrical connection is made. The electrical connection for this DMD utilizes a land grid array. Micro pin grid array and board-to-board connectors are utilized on other DMDs. The thermal interface is an area on the DMD that is contacted directly to cool the DMD. Datums A, B, and C should be used when mounting the DMD for most accurate alignment. Electrical interconnect basics. DMDs with board-to-board connectors mate with connectors that are soldered on a PCB. These connectors have both self-alignment and retention features. DMDs with micro pin grid arrays mate to sockets that are soldered on a PCB. The pins in the DMD self-align to the contacts in the socket. DMDs with LGA pads and open notch style datums do not have direct alignment between the DMD and the mating interposer. Alignment is accomplished using indirect reference features. The DMD is aligned to the optics chassis and then interposer aligned to the optics chassis. It is important when mounting a DMD with an LGA interconnect to always maintain uniform pressure to ensure a good electrical connection. DMDs with LGA pads and edge-style datums utilize interposers which have features that align the DMD to alignment pins on the interposer. The interposer alignment pins are then used to align the interposer to the PCB. Again, Uniform pressure is needed to ensure a good electrical connection. The size of the thermal interface is determined by the opening in the electrical interconnect. DMDs with the same series number are considered in the same DMD family and have common features, utilize the same mounting concepts and electrical interconnect. DMDs that share the same series number have the same ceramic size, mounting datums A, B, and C, array center relative to mounting datums A, B, and C, window thickness, illumination direction, thermal interface, electrical interface. The only exception are the automotive DMDs, which are called Series 450, but the array center is not in the same position as the other Series 450 DMDs. DMDs with the same series number can have different array sizes, resolutions, pixel sizes, distance from array to window, and electrical interface and pin signal assignments. Typically, the same optical engine can be used for DMDs in the same family, with the only mechanical change needed being a different illumination integrating tunnel or rod. The title block on the DMD mechanical ICD drawing indicates the DMD series number and package reference designator. The ICD drawing can be found at the end of the DMD datasheet. The series number of the device is used to identify the detailed mounting concept for a particular DMD. An example is a Series 410 mounting concept will work for all Series 410 DMDs. DMDs with the same ceramic size share common features, but not to the extent the series family do. The most common ceramic sizes are a 0.7 size and a 0.9 size. Common features within each size include datums A, B, and C, and the array center relative to the datums. The same size ceramics do not have the same electrical interface or the number of pins or pad locations. Information in a datasheet of specific interest when doing a mechanical design of a system using a DMD includes the mechanical interface control drawing, which has the nominal geometry of the DMD and the tolerances of the features. The mechanical ICD is located at the back of the datasheet. The maximum loads or forces that can be applied to the electrical and thermal areas when mounting the DMD, the recommended thermal conditions, array temperature calculation, standard thermal test points, and a temp sensor information. Note that not all DMDs have a temp sensor. Important considerations when mounting DMDs include alignment of the array, establish and maintain a good electrical connection, control of mechanical forces applied to the electrical and thermal interface areas such that they do not exceed those in the datasheet. The methods to control the mounting loads include by design of features, which is the best and most repeatable. Features of the design are designed to prevent excess loads from being applied to the DMD without relying on assembly process steps. This type of design minimizes force variation and allows the range of forces to be controlled and determined by simple calculations. Control of loads using an assembly procedure or process will have greater force variation and highly dependent on the person doing the assembly. This method typically relies on the torque of a fastener to control the applied loads. Mounting designs that control the loads by the design features rather than rely on screw torques or assembly processes are the best and most reliable. The first example utilizes two concentric coil springs. Torque on shoulder screws is not critical to controlling the loads applied. The clamp prevents the PCB from bowing, which can result in electrical connection issues. The stiffness of the material and thickness are important. The insulator prevents capacitive coupling of the PCB signals when using a metal clamp. Coil spring number 2 controls the load on the electrical interface area. The spring rate of the spring and size of the gap in which it fits are important to control the load. The nominal and range of forces are easily calculated when using coil springs and shoulder screws. Coil spring number 1 controls the load on the thermal interface area. The spring rate of the spring and size of the gap in which it fits are important to control the load. The nominal and range of forces are easily calculated when using coil springs and shoulder screws. This design uses a second set of shoulder screws, which allows the electrical connection to be secured before adding the heatsink. The second example utilizes coil springs and a flat spring. As in example 1, torque on shoulder screws is not critical for the control of loads applied. The clamp prevents the PCB from bowing, and the insulator prevents capacitive coupling of the PCB signals when using a metal clamp. Coil springs control the load on the electrical interface area. The spring rate of the spring and size of the gap in which it fits are important to control the load. The flat spring controls the load on the thermal interface area. The size and variation of the gap the spring fits and characteristics of the spring are important. Finite element analysis and testing of springs is generally required to determine the nominal and range of loads. Mounting designs that control loads using torque on screws and an assembly procedure or process have greater variability in the loads applied and are dependent on the assembly personnel. This example utilizes a flat spring and torque on screws. As in previous examples, the clamp prevents the PCB from bowing, which can result in electrical connection issues. The insulator prevents capacitive coupling of the PCB signals when using a metal clamp. The flat spring controls the load on the thermal interface area. The size and variation of the gap in which the spring fits and characteristics of the spring are important. Finite element analysis and testing of springs are generally required to determine the nominal and range of loads. Torque on screws and assembly procedure control load on the electrical interface area. The torque on the screws is very critical to control the load. The screw clamping force has a large variation driven by the tightening procedure, condition and material of the screw, and the material the screw is threaded into. Partial tightening and special order of tightening of fasteners and/or the use of a fixture are typically required to achieve a uniformly applied load which avoids stress concentrations on the ceramic. This concept illustrates mounting a DMD that has open notch datums, an LGA electrical interconnect, and controls the loads applied to the electrical and thermal areas using design features. To align the DMD to the optics chassis requires the DMD datums B and C be pushed against corresponding features on the optical chassis and held in place while the assembly is completed. The shims keep the datums aligned during the assembly. This alignment is critical to both the electrical connection as well as the optical alignment of the array. The electrical connection between the DMD and the interposer is done indirectly by aligning holes in the interposer to pins on the optics chassis. The electrical connection between the interposer and PCB is done directly using interposer pins and round holes in the PCB. Some DMDs utilize an interposer without alignment pins. In these cases, the pins on the optics chassis are used to align two holes in the PCB. The DMD, interposer, and PCB are clamped together using shoulder screws and compressible washers to control the loads applied to the DMD electrical interface. The clamp provides sufficient stiffness to prevent the PCB from bowing. Bowing of the PCB can result in electrical connection issues. The use of coil springs rather than compression washers is a simpler option to consider. The heatsink is secured in place using shoulder screws and coil springs to control load on the thermal interface area. The coil spring and gap in which it fits are designed to meet the thermal performance requirements without exceeding the maximum loads on the DMD thermal interface. Additional support may be required for large, heavy heatsinks to prevent them from moving during vibration and shock conditions. Any additional support should be done in a manner such that the loads on the DMD are not increased above the specifications. This concept illustrates mounting a DMD that has hole and slot datums, a micro pin grid array electrical interconnect, and controls the load applied to the thermal area using design features. The DMD electrical pins are inserted into the socket which has previously been soldered to a PCB. No force is needed on the DMD electrical interface to ensure good electrical connection. The only force needed is to keep the DMD and socket from separating during vibration or shock conditions. This can easily be accomplished with little or no force applied to the DMD. The DMD datums B and C are placed over round pin features on the optics chassis to provide alignment of the array to the optical pins. The heatsink is secured in place using shoulder screws and coil springs to control the load on the thermal interface area. The coil spring and gap in which it fits are designed to meet the thermal performance requirements without exceeding the maximum loads on the DMD thermal interface. Additional support may be required for large heat sinks to prevent them from moving during vibration or shock conditions. Any additional support should be done such that the loads on the DMD are not increased above the DMD specifications. This concept illustrates mounting a DMD that has datums on the edge of the ceramic, an LGA electrical interconnect, and controls the loads applied to the electrical and thermal areas using design features. The DMD is inserted into the interposer, which aligns the DMD to the interposer contacts. The interposer has spring arms that push the DMD datums B and C against corresponding features on the interposer. Pins on the interposer are inserted into holes in the optics chassis to align the DMD to the optical components. The holes in the PCB are placed over pins on the interposer to align the PCB pads to the interposer contacts. The DMD interposer and PCB are clamped together using shoulder screws and coil springs to control the loads applied to the DMD electrical interface. The coil spring and gap in which it fits are designed to meet the compression requirements of the interposer contacts without exceeding the maximum limits on the DMD electrical interface area. The coil springs also ensure the load on the electrical interface area is applied uniformly. The clamp provides sufficient stiffness to prevent the PCB from bowing. Bowing of the PCB can result in electrical connection issues. The heatsink is secured in place using shoulder screws and coil springs to control the load on the thermal interface area. The coil spring and gap in which it fits are designed to meet the thermal performance requirements without exceeding the maximum loads on the DMD thermal interface. Additional support may be required for large, heavy heat sinks to prevent them from moving during vibration and shock conditions. Any additional support should be done such that the loads on the DMD are not increased above the DMD specifications. Detailed mounting information is available on TI.com. To locate the information, open a web browser to www.ti.com and enter the DMD part number in the search field. This example uses the DLP660TE DMD. Pick the DMD name or picture, pick Design and Development tab, pick Design Tools and Simulation tab. A 3D CAD model of the DMD in step format can be downloaded. The Mounting and Electrical Interconnect download is a zip file which includes mounting considerations, assembly and part drawings, 3D CAD files, and information on the electrical interconnect part and supplier. Note the series nomenclature in the titles. The downloaded zip file of the DMD mounting design will need to be extracted before use. Use the Extract All to gain access to the individual files using a web browser. Open the README file to get started. If the Extract All was successful, an exploded view of a mounting concept will be displayed at the bottom. If an exploded view is not displayed, the Extract All was not completed successfully and should be repeated. Pick the Review Start or image link to start reviewing the information. Links to detailed information include the DMD datasheets, mechanical ICD drawings, and 3D CAD models. Electrical interconnect information includes a TI drawing of the reference geometry, a 3D CAD model, and supplier information. Pick link to get mounting concept options and important considerations. Pick a mounting concept title or picture for the detailed drawings and 3D CAD information.